Hiya, welcome to another Astronomy with Claire. Sorry I look a bit of a mess. It's been a hot, long day out kayaking, shopping, all sorts of stuff. But tonight's a very clear night, and after the success of the previous video when it came to shooting Jupiter and Saturn from a bit of a distance, and then that amazing up close image of Jupiter, I kind of want to do the same tonight but with Saturn. So as you can see, everything is up and running. Telescope is polar aligned, and I'm doing plate solving at the minute. As you know, that's the are we there yet method for finding our way around the sky. So I've currently pointed out, because Saturn hasn't risen yet, it's rising, it's just about coming up over the trees, so it's going to take a little while for us to be able to image it. And I've now instructed the telescope to move over to Saturn, and just over to the left you'll see there's Jupiter as well, so we'll be looking at Jupiter in a moment. Okay, so I wonder if I can tell. Oh no, done all that wrong. Bit excited. Okay, so let's do a 5-second exposure of the area that could roughly be Saturn, hopefully. Let's see what happens. Okay, well, we're spot on. We couldn't be any more spot on unless we were in the middle of the picture. So here's Saturn. We've exposed for 5 seconds, a very bright, shiny object, so it shines. You know, we've captured a lot of light. But what it does do is it shows here the Saturn moon system. So if we bring up Stellarium and we zoom in, we should be able to see some of those moons. So if I pause this, so we'll see if we can compare that to the actual image. So it's depending which way round the image is. So Titan is very bright and far out. So it could be Dion is this one, Titan is this one here, Tethys, not sure, Enceladus, I don't know. But okay, let's go like that and take it off pause. Go to now. Okay, and take it off full screen. Okay, we'll do that. Okay, so 5 seconds is obviously way too bright, so we do it for 1 second to see what happens. Camera decides to mess up. Go back to 1 second. Stop that. I'll have to switch it off, switch it back off again, on again. Okay, camera, switch off. Disconnect the camera. Switch it back on again. If it doesn't work, switch it off, switch it back on again. Okay, 1 second. Okay, let's try 2 seconds. Okay, Nina's not well suited for doing planetaries, so I'm going to do switch off here. Yes, I do. I'm going to switch off the focuser because we're going to need that too. And then we're going to go to SharpCap. So SharpCap is the software we used last time to basically take video clips of the objects rather than long exposures as we do for galaxies and nebula. The very bright planets need just short images, but if you just do one, it may not turn out to be sharp enough because of the air vibration. So the best way to do it is a compromise, is to take lots of photographs and try and find the best ones where the air is still enough. So cameras, I've started the wrong camera. Silly Billy. There's two cameras on the telescope. One is for guiding, which I haven't tried just yet. So here we go. And straight away you can see Saturn is in the view. So overexpose, you can see some of the moons there, but straight away you can see, if I reset this, even at 100 milliseconds, Saturn is most definitely in the view. So let's zoom at, so this is not camera 100%, this is camera 100%. So you can see most definitely there is the ring system. There's even the little bit of a bump underneath the rings where, because the rings are so thin that the actual planet is sort of poking out from underneath and again over the top. You definitely can see the division between the rings and the planets. Let's see if we can go 150. Let's give us a little bit closer. You can see some banding on the planets there, going across, some lighter here and darker at the top, which is amazing. It's just, that's just brilliant. Even at say 100 milliseconds. So what we can do is we can, let's reduce this to 50. We can reduce the camera area that we want to capture, because it's such a small area. It doesn't matter if the rest of it's not captured, it's because we're not aiming for anything there. So if we go right down to 640 by 480, and then we want to concentrate on this part of the picture, so bring in Saturn to roughly the middle, and then what we can do is, so off it goes. So it's now capturing 1,000 frames of Saturn at 10 frames a second, which is great. So it shouldn't take us too long to get our image, and then I hope to then go for the Barlow, which gives us 5 times closer like we did with Jupiter. Now Saturn is a lot further away. It is 1 billion kilometers, whereas I think, how far is Jupiter? Okay Google, how far is Jupiter from Earth?
Jupiter and Earth are currently about 624,430,000 kilometers apart.
Okay, so
they follow elliptical orbits around the Sun, and the distance is constantly changing.
Okay.
Would you like to hear more?
No thank you, Google.
I'll be here.
That's okay. And I expect, if any of you got any Google software or anything, it's probably answering you right now if you're listening to this. But 624 million kilometers for Jupiter. Okay, Google, how far is Saturn from Earth?
Saturn and Earth are currently about 1,339,500,000 kilometers apart.
1 billion?
Elliptical orbits around the Sun.
Okay, Google, cancel. 1 billion kilometers away. So this image we're looking at right now, which is live, is 1 billion kilometers away, which is amazing, utterly amazing. So what I'm going to try and do now is I'm going to attempt to put Saturn right in the center of the view. So this is what I did with Jupiter. Move Saturn right into the center of the view, like so. So I'm very, very slowly, carefully moving the telescope with these controls. No, it's the wrong way. Okay, very, very gently, very, very gently. Okay, so it's roughly in the middle. And then what I'm going to do now is pause the video. I'm going to go and put the Barlow in there, which is the like a large tube which the camera slots into, and let's see what we can get. Okay, so that's now in there. This tube is now in. So basically I've taken the camera out of the telescope, inserted the large 5x Barlow lens, and then put the camera back in there. But then what that does is any adjustments to the light train, as it's called, the light going at one end of the telescope and all the way through, affects the focus. So instantly we've lost the picture. So what we have to do now is essentially find the planet again. We know it should be roughly in the center of the screen. So what I can do is stretch the histogram, then bring up the exposure. So already I can see something. Here we go. So it looks like we're quite lucky that we haven't really nudged the telescope. That's one of the things, is nudge the telescope or anything like that. So we've got definitely something. We've also got dirt. These little dots here are essentially dirt on the lens or on the camera that have to be, you can either clean them off or have to be removed in post-processing. So we're very gently moving the telescope to get this blob into the center of our picture again, and it will turn from a very large blob into a much smaller blob when it goes into focus. But basically what I want is it very roughly in the center of our screen. I mean, there are many different ways of doing this, and many other astronomers will tell you different things, but this is the way I do it. It's a lot easier to find something if it is out of focus, especially planets. There we go. We can see Saturn. We can see it's very, very bright. So what I'm going to do is change down the exposure so it's not so bright. Change the histogram so it's no longer stretched, but we can definitely see now Saturn and its rings are there in front of us, which is great. So let's get a bit more focus. 50. Now, if we were at the telescope itself, looking through it with your own eye, what you'd simply be able to do is just adjust it with your own eye. And this is what in most telescope setups you will do, is simply look through it with your own Mark 1 eyeball and adjust it until basically it comes into focus. The setup I have here is that everything is remote. The telescope is out in the garden. I don't get cold, but I then have to do everything electronically and rely on the equipment. So let's reduce this to 150. So we move even slower. So the lower this number is, the smaller the amount that it brings into focus. So okay, so we want, let's move at increments of 100. I think this is the best focus I can get for an object that's 1 billion kilometers away. That's pretty good, I think. I mean, you can see the different cloud belts around the planet. It's a little bit more featureless than Jupiter, but you can see the distinctive rings and that there is the big division between the rings and the planet itself. And sometimes you may be able to see another division between this ring and this part of the ring, and that's about 3,000 kilometers across. The rings are many times the size of the Earth in width, as is the planet itself. So what I'm going to try and do is, before it creeps away, is get some frames on it. So I can then analyze this and then hopefully come up with a good picture. So, okay, so it's now recording 500 frames of Saturn, like so. So as you can see, the atmosphere wobbling and the air distortions. So some of the frames look good, some of the frames look bad, and it's capturing at around 3 frames every second. So as a second goes past, we're going to get, as I say, three seconds, and hopefully then the processing software afterwards will allow us to take all of these frames, work out which ones are the worst, get rid of them, and then work out which ones are the best, and keep them, and then we'll be able to have a good picture at the end of it. So it looks like Saturn's getting quite dim now. It may be because I think it was heading towards a tree, so it may be going behind some leaves or something. I'll turn the exposure up. Yeah, it looks like it's very easily that planets and items can end up going behind trees and things like that. So what we will do now is we will slew over to Jupiter. Move Jupiter to here and then click on it. So we're going to, and this should be interesting, seeing as we've got the 5 times Barlow in. I doubt very much we will see it. The telescope is moving. Here it goes. We would be extremely lucky if Jupiter suddenly appeared in front of the camera. Okay, we were extremely lucky. Kind of wasn't expecting that. So okay, the camera's the telescope's fairly accurate. Right. Okay. Well, Jupiter's a lot brighter because it's a lot bigger, and also a lot closer to us. And ooh, blimey. So let's use the telescope controls to move Jupiter into the center of the view. You can also see a moon here. There is a moon quite close to Jupiter. Possibly that is Io. So let's see what we can see. So obviously it's very overexposed. What was adequate exposure for Saturn, because it's so far away, even though it's still a bright object, is way overexposed for Jupiter. So we just need to bring down the exposure for Jupiter and the gain as well, until we get basically we get Jupiter. So we can definitely see the markings on there, and we got also what is possibly, which is great, a shadow. So in the same way that any object, any object can cast a shadow onto something else, there's a very good possibility. So let's see, I've got a whiteboard here. So basically, okay, so let's get one of the pens out. So I've been planning this for a little while, but I hadn't got a pen prepared. Okay, so what we're currently looking at, it looks like, is here is Jupiter, and it has many moons. The four main ones that you can see are Io, Ganymede, Callisto, and Europa, or Europa and Callisto. They're the four brightest ones that can be seen. Now, sunlight is coming from the sun, and sometimes a moon is in the right position that it causes a shadow to be shown on the surface of there goes the pen lid, of the planet. So that's essentially what you are seeing there. So get the pen lid, and oh, rather exciting. So here we have, let's turn up the exposure. Definitely, look at that. There is 100% a shadow on the planet. So there's the moon there. And if we underexpose, you can see there is a shadow on it. The great red spot, it looks like here is the great red spot. So we can turn down the exposure a bit. So this is a gigantic hurricane, the 3 times the size of the Earth. So the Earth will fit 3 times inside it, which is amazing by itself. So we're going to turn down the gain just a little bit. Okay, so a bit more of a focus, and if I turn up the analog gain, which is a bit like the ISO on a DSLR, you can see there is a moon and it is projecting a shadow onto the planet's surface, which is amazing to watch. It's a bit like when there is an eclipse on Earth. The shadow is passing across the surface of this planet as we look at it right now. This is happening right now. This is planetary physics in motion as these tiny little worlds go around Jupiter and cast shadows onto its surface. So I'm going to turn down the gain a bit. So we've got the detail of the bands, and the great red spot is very clearly here. Okay, so what I'm going to try and do now is, it's not capturing it, quick capturing at many frames per second, so we're going to say Jupiter with shadow 5 times, and the date is now the 18th. It's gone past midnight. 07:21. Okay, and let's start. Quick capture. So now we are basically recording 1000 frames, and these 1000 frames are going to be used in the analysis of this picture to work out the best possible frames to use, which ones are the worst ones, and yeah, so this will aid us to do the best possible picture that we can. Some more information about Jupiter whilst we're capturing this is that the planet rotates so quickly. For something so big, it takes 10 hours to go around on its axis compared to our 24, which I've mentioned before. But this is really noticeable because Jupiter is covered in clouds. It's vast cloud belts of different chemicals that cause these different clouds and shapes and storms. And we can see literally how fast Jupiter is rotating, by how quickly these shapes go around the planet, especially the Great Red Spot. In literally a few hours, that Great Red Spot will move from here to further around either one side or the other. Depends which way round it's rotating, I'm not sure. But the moons are also going around with the moon, going around with the planet, and this dot will move across. If it was to come back in an hour, that dot will either be a bit further to the left or a bit further to the right, as the planet is rotating, which in itself is just amazing to watch. So I'm just capturing 1,000 frames. It's going to take just a couple of minutes. And one of the other things that you have to be aware of when capturing images of Jupiter is that if you capture for too long, Jupiter rotates, as we've been saying, but rotates because of its speed of rotation. Which the start of the video that we've captured shows Jupiter in one position, and at the end it's in another position. I mean, that's over dramatizing it, but it's basically then produces like a blurring effect because it simply rotated so quick, and we've been capturing a lot of video over a particular period of time. So it's a bit of a balance between how many frames you capture in order to produce detail compared to how much rotation you capture during the recording. So the more frames the better, but in Jupiter's case you'll end up with more rotation effect. But it's beautiful when you look at it now. It's utterly beautiful. There's a band here, this big this is the northern equatorial belt, so this is the Great Red Spot, the lower equatorial belt. Jupiter's made up of lots of different chemicals, but primarily the same chemicals that make up our sun, hydrogen and helium. It would have been another star if it had been a little bit more dense, and the pressure inside may have caused nuclear fusion to take place, and when that happens, hydrogen starts being compressed into helium, which then becomes a star. That process causes a release of energy, resulting in a star like our sun. It's just Jupiter was a little bit too small for that to happen. It is suspected underneath those cloud belts, hydrogen and helium is being compressed so much that it's actually become a liquid, and there is liquid hydrogen and helium around a sort of a hard rocky core, but nobody really knows. That it is just scientific theory at the minute. But we've captured 1,000 frames, so that's worth going to have a look at, and a bit of a process. And so you can look at that. You can see that there is a direct line. So this could well be Ganymede causing this shadow. So if we turn down the exposure, we can see that Ganymede, if that is Ganymede, is causing a shadow across the planet. The view is quite amazing. There's the Great Red Spot, there's the shadow, the other cloud bands, and there is the moon. So what I'm going to do is I'm going to capture another one. Okay, so there we have it. It's another night of gas giants with the telescope and the 5x Barlow lens. Here we had Saturn, amazing shots of Saturn with the rings. Here we have an amazing shot of Jupiter with the Great Red Spot, which does seem to have moved slightly. The shadow of more than likely Ganymede, causing the shadow onto the planet. So yeah, so I'm going to say it's a fairly successful evening. I'm going to go ahead and analyze these images now, and see what happens next. Okay, until next time. If you like the video, remember to like it. Please share it if you think others would want to see this. Hit subscribe, and the little bell will tell you when more videos have been released. And I'll see you in the next one. See you later. Bye.